Building envelope metrics. Welcome to Building Envelope Metrics, where we explore the critical elements that define a building's performance. This course covers the design, components, and systems that shape energy efficiency, comfort, and durability. Join us as we delve into the foundation of effective building management. Building envelope. The building envelope is the physical barrier between the conditioned interior and the unconditioned exterior environments. It encompasses the roof, walls, windows, doors, and foundation, serving as the first line of defense against external weather conditions. The design and materials used in the building envelope significantly impact energy efficiency, comfort, and durability. A well-designed envelope minimizes heat loss and gain, contributing to lower energy costs and improved indoor air quality. Building components. Building components refer to the individual parts that make up the structure, including structural, thermal, and protective elements. These components work together to create a cohesive and functional building. Key components include walls, roofs, windows, doors, and foundations, each contributing to the building's overall performance and resilience. Understanding how these components interact is crucial for effective building design and energy management. Building interior. The building interior encompasses all spaces within the building, including rooms, hallways, and common areas. Interior design focuses on creating functional, comfortable, and aesthetically pleasing environments for occupants. It includes the selection of finishes, furnishings, and layout. Effective interior design also considers acoustics, lighting, and thermal comfort, contributing to a positive occupant experience. The interior is shaped by the building envelope and its performance. Building exterior. The building exterior refers to the outer surface and facade of the structure, which protects against weather elements while contributing to aesthetics. It includes walls, roofing materials, windows, and doors. The choice of materials and design influences energy efficiency, insulation, and maintenance needs. A well-designed exterior not only enhances curb appeal but also plays a critical role in the building's thermal performance and durability against environmental factors. Heating. Heating systems are essential for maintaining comfortable indoor temperatures during cold weather. They can include central heating systems, such as boilers or furnaces, as well as localized heating solutions like space heaters. Effective heating design considers the building's thermal envelope to minimize heat loss and optimize energy use. Various heating methods, including hydronic, forced air, and radiant heating, are utilized based on building type and climate requirements. Cooling and ventilation. Cooling and ventilation systems work together to maintain indoor air quality and comfort during warm weather. Cooling can be achieved through air conditioning systems, evaporative coolers, or passive design strategies such as cross-ventilation. Proper ventilation ensures the exchange of indoor air with fresh outdoor air, reducing pollutants and humidity levels. Effective design balances cooling needs with energy efficiency, enhancing occupant comfort and health. Uninsulated. Uninsulated ducts are conduits for air distribution that lack thermal insulation. This can lead to energy loss as conditioned air may heat or cool while traveling through uninsulated spaces, reducing system efficiency. Insulating ducts is crucial in maintaining temperature and improving energy performance in HVAC systems. Proper insulation minimizes heat transfer, ensuring that conditioned air reaches its intended destination without significant temperature changes. Pipes. Pipes are essential for transporting fluids, such as water for heating, cooling, and plumbing systems. Their placement and insulation are critical for preventing heat loss or gain in hydronic systems. Properly insulated pipes enhance energy efficiency and reduce the risk of condensation or freezing in colder climates. The design and materials used for piping systems must consider flow rates, pressure, and the thermal properties of the building envelope. Heating equipment. Heating equipment includes all devices used to generate heat, such as boilers, furnaces, heat pumps, and radiators. The selection of heating equipment depends on building size, climate, and energy sources available. Efficient heating equipment is designed to optimize energy use while providing consistent comfort levels. Regular maintenance of heating equipment is crucial for ensuring reliability, safety, and longevity, contributing to overall system performance. Heat transfer. Heat transfer refers to the movement of heat energy between different areas within a building or between the building and its environment. It occurs through conduction, convection, and radiation. Understanding heat transfer is essential for effective building design, particularly in optimizing insulation, windows, and other envelope components. Strategies to minimize unwanted heat transfer can enhance energy efficiency and occupant comfort. Wall and window. Walls and windows are critical components of the building envelope, influencing thermal performance and daylighting. Walls provide structural support and insulation, while windows allow natural light and views. The choice of materials and construction methods affects heat gain, loss, and overall energy efficiency. Proper placement and selection of windows enhance daylighting and ventilation while minimizing heat transfer, contributing to a comfortable indoor environment. Doors and roof. Doors and roofs play crucial roles in the building envelope, impacting security, access, and thermal performance. Doors provide entry points while contributing to insulation and air sealing. Roofs protect against weather elements and can also influence energy efficiency through their design and materials. Roof insulation and reflective surfaces can reduce heat gain and loss, while proper door selection ensures airtightness and energy savings. Building foundation. The building foundation supports the structure and protects against moisture intrusion from the ground. It plays a critical role in maintaining the building's stability and longevity. Foundations can be designed as slab-on-grade, crawl spaces, or basements, each influencing thermal performance and moisture control. Proper insulation and drainage systems are essential to prevent heat loss and moisture problems associated with foundations. Skylights. Skylights are windows installed in the roof to allow natural light into a building. They enhance daylighting and can reduce reliance on artificial lighting. Proper placement and design of skylights are crucial for minimizing heat gain and loss, as well as preventing glare and overheating. Skylights contribute to the building's aesthetics and can improve occupant well-being by providing a connection to the outdoors. Dampers. Dampers are devices installed in ducts or vents to regulate airflow within HVAC systems. They can be manually or automatically operated, controlling the volume of air entering different areas of the building. Proper damper design is essential for balancing airflow, improving energy efficiency, and maintaining indoor air quality. Dampers are integral to zoning systems, allowing for tailored comfort levels in different spaces. Building load. Building load refers to the total amount of heat energy that must be added or removed to maintain comfortable indoor conditions. It encompasses heating, cooling, ventilation, and internal gains from occupants and equipment. Calculating building load is crucial for designing HVAC systems that efficiently meet occupant needs while minimizing energy consumption. Accurate load assessments ensure proper sizing of heating and cooling equipment. Thermal insulation of buildings. Thermal insulation reduces heat transfer between the interior and exterior of a building, enhancing energy efficiency and comfort. Insulation materials can be applied to walls, roofs, and floors, with various types including fiberglass, foam, and cellulose. Proper insulation installation is vital to prevent air leaks and thermal bridging, which can compromise performance. Effective insulation contributes to lower energy bills and improved indoor climate control. Dehumidifier of air. A dehumidifier removes excess moisture from indoor air, improving comfort and preventing mold growth. It works by condensing humidity from the air, which can be particularly beneficial in humid climates or during hot weather. Dehumidifiers contribute to indoor air quality by maintaining optimal humidity levels, enhancing occupant health. Integration with HVAC systems allows for automated humidity control in residential and commercial buildings. Dry and wet bulb thermometer. Dry and wet bulb thermometers are used to measure air temperature and humidity. The dry bulb thermometer measures the ambient air temperature, while the wet bulb thermometer, which has a moist wick, indicates the cooling effect of evaporation, helping determine humidity levels. These measurements are essential for designing HVAC systems and understanding indoor climate conditions. Accurate readings support effective energy management and occupant comfort. Space temperature sensor. Space temperature sensors monitor and control the temperature within a designated area of a building. They provide real-time feedback to HVAC systems, allowing for precise temperature regulation. Accurate sensors are essential for maintaining comfort and energy efficiency, ensuring that spaces are heated or cooled as needed. These sensors play a key role in smart building technology, enabling automated climate control. Partitions. Partitions are interior walls that divide spaces within a building without contributing to the structural integrity. They can be permanent or movable, allowing for flexible space usage. Proper design of partitions influences acoustics, privacy, and airflow. Partitions can also be insulated to enhance thermal performance and comfort, contributing to energy efficiency and occupant satisfaction. Plenums. Plenums are spaces within HVAC systems that serve as distribution areas for air. They can be located above ceilings or below floors and connect ductwork to supply or return air. Proper design of plenums is crucial for efficient airflow and system performance. Plenums can also act as mixing zones for conditioned air, ensuring balanced distribution throughout a building. Effective plenum design enhances energy efficiency and comfort. Air infiltration. Air infiltration refers to the uncontrolled movement of outdoor air into a building. This occurs through leaks, cracks, and openings in the building envelope, leading to increased energy costs and reduced indoor comfort. Effective sealing measures, like weather stripping and caulking, are essential to minimize air infiltration, optimizing HVAC performance and enhancing energy efficiency. Lights. Lighting is crucial in building design, impacting both aesthetics and energy consumption. Different types of lighting, ambient, task, and accent, affect occupant comfort and productivity. Energy-efficient options, such as LED fixtures, help reduce energy use. Designing with natural light sources in mind further improves energy performance. Acme, small office building. Acme serves as a model small office building, showcasing effective building envelope design and performance. Emphasizing energy efficiency, comfort, and functionality, factors such as insulation, window placement, and HVAC systems are vital. Analyzing Acme helps identify best practices for energy-efficient design. Office desks with PC. Office desks with PCs contribute to internal heat gains, affecting the building's cooling load. The placement of desks impacts workspace ergonomics and energy use. Planning ensures desks maximize natural light while minimizing glare, crucial for effective HVAC design. This image highlights essential office items, with the left panel presenting an office essentials checklist featuring key components like task lighting, computer, desk, chair, whiteboard, paper shredder, communication tools, internet connection, safe, file organizer, and a printer copier scanner. The right panel complements this by showcasing a collection of office supplies, including pens, markers, sticky notes, paper clips, staplers, scissors, tape dispensers, and calculators, emphasizing the practical tools needed for a functional and efficient workspace. The U-value measures the rate of heat transfer through building elements like walls and windows. A lower U-value indicates better insulation performance, reducing heat loss in winter or heat gain in summer. Understanding U-values helps select materials that enhance thermal performance. U-value vs. R-value. What they measure. U-value measures the insulating performance of glass. Lower U-values indicate better insulation, less heat loss. R-value measures the thermal resistance of other building materials. Higher R-values indicate better insulation, more resistance to heat flow. Relationship. U-value and R-value are mathematical reciprocals. This means that they are inversely proportional to each other. To convert U-value to R-value, divide 1 by the U-value. To convert R-value to U-value, divide 1 by the R-value. Example. If a window has a U-value of 0.10, its R-value is 1 divided by 0.10 equals 10. If a wall has an R-value of 3.45, its U-value is 1 divided by 3.45 equals 0.29. Radiant floor heating. Radiant floor heating circulates warm water or electric cables beneath the floor, providing even heat distribution and enhanced comfort. Operating at lower temperatures than conventional systems, it is energy efficient and particularly effective in spaces with high ceilings or large windows. Solar heat gain via glass. Solar heat gain occurs when sunlight enters a building through windows, raising indoor temperatures. Factors such as glazing type, orientation, and shading devices affect this gain. Managing solar heat gain is crucial for maintaining comfort and reducing cooling loads. Attic insulation. Attic insulation prevents heat loss in winter and heat gain in summer. Proper insulation maintains consistent indoor temperatures and enhances energy efficiency. Various materials like fiberglass or spray foam can achieve desired thermal performance, reducing the workload on heating and cooling systems. The impact of urbanization on heating and cooling degree days. The image shows the relationship between urbanization and the number of heating and cooling degree days experienced in different areas. Observations. Heating degree days. The number of heating degree days decreases as urbanization increases. This is likely due to the heat island effect, where urban areas tend to be warmer than rural areas. Cooling degree days. the number of cooling degree days increases as urbanization increases. This is also likely due to the heat island effect, as urban areas experience higher temperatures. The image highlights the impact of urbanization on the climate of an area. As more and more land is converted to urban areas, we can expect to see a decrease in heating degree days and an increase in cooling degree days. Wall insulation. Wall insulation reduces heat transfer through the building envelope, enhancing energy efficiency and comfort. It can be installed as batts, blown-in insulation, or rigid foam panels. Proper installation minimizes thermal bridging and air leakage, ensuring consistent indoor temperatures. Windows installation. Proper installation of windows ensures airtightness and thermal performance. Poorly installed windows can lead to air leaks and condensation. Techniques like flashing, weather stripping, and sealants create a weather-tight seal, contributing to energy performance and occupant comfort. Shade window treatment. Shade window treatments, like blinds or curtains, help control sunlight, reducing heat gain and glare. They enhance occupant comfort and improve energy efficiency by minimizing reliance on cooling systems, optimizing natural light while maintaining comfortable temperatures. Films window treatment. Window films reduce solar heat gain and glare while maintaining visibility. They can enhance window thermal performance without replacement. Available in various tints, window films allow customization based on building needs and aesthetic preferences. Screen window treatment. Screen window treatments consist of mesh materials that block sunlight and insects while allowing airflow. They reduce heat gain and glare, enhancing indoor comfort and energy efficiency. Their lightweight design makes them practical for improving energy performance. Ventilation. Ventilation exchanges indoor air with outdoor air to maintain air quality. It removes pollutants and introduces fresh air. Methods include natural, mechanical, and hybrid systems, balancing ventilation with energy efficiency to maintain a healthy indoor environment. Infiltration and exfiltration. Infiltration is the unwanted entry of outdoor air, while exfiltration is the escape of conditioned indoor air. Both impact energy efficiency and indoor air quality. Proper sealing of the building envelope is essential for minimizing these processes, which helps control heating and cooling costs. Door sweeps. Door sweeps reduce air leakage between doors and floors. They minimize drafts and improve energy efficiency by preventing unwanted air from entering or leaving. Proper installation enhances indoor comfort and can lower energy costs, especially in exterior doors. Caulking. Caulking fills gaps and cracks in the building envelope, preventing air leaks and water intrusion. Essential for energy efficiency and moisture protection, caulking should be regularly inspected and maintained to ensure a tight building envelope, enhancing occupant comfort. Exhaust fan. Exhaust fans remove stale air, moisture, and odors from indoor spaces, improving ventilation. Found in kitchens and bathrooms, proper sizing and placement are essential for effective operation. These fans contribute to overall ventilation strategies, supporting a healthier indoor environment. Vestibule. A vestibule is an enclosed space between the entrance and exterior, reducing air infiltration. They maintain indoor temperatures and are effective in extreme climates, enhancing energy efficiency and occupant comfort. Proper design improves entrance aesthetics while providing functional benefits. HVAC system. The HVAC system controls indoor environmental comfort through heating, cooling, and ventilation. An effective system integrates components for optimal performance and energy efficiency. Proper design and maintenance are crucial for comfortable conditions while minimizing energy consumption. Heating load components. This image shows a simple room with several sources of heat loss. Infiltration and ventilation. Air from outside can leak in through cracks in the walls and windows. This air is typically colder than the air inside, so it needs to be heated. Glass conduction. Heat can be lost through windows and other glass surfaces. Exterior wall. Heat can also be lost through the exterior walls. Partition wall. The partition wall separates the room from an adjacent space, and heat can be lost through this wall as well. Floor. Heat can be lost through the floor. Thank you for your attention. For more details, please contact TSD Office Engineering GHG. We appreciate your interest in ESG initiatives.